Welcome to This Explainer. Today, we are putting on our detective hats. Molecular detective hats, that is. We're going to try and piece together the identity of an unknown chemical suspect by exploring the totally fascinating world of mass spectrometry. And specifically, we're focusing on exactly how we determine the true molecular weight of a compound. So to kick off this mystery, we've got to ask a question that honestly sounds kind of impossible, but it's something scientists face every single day. If you have an unknown microscopic substance, how on earth do you figure out exactly how much it weighs? And by extension, what it actually is? Right, so here is the central mystery. We are going to figure out a molecule's exact weight by examining nothing but the shattered pieces it leaves behind after being completely obliterated. I know, it sounds totally counterintuitive, right? But in chemistry, breaking a molecule apart is actually the absolute best way to figure out how it was put together in the first place. All right, part one, the molecule shattering machine. Our investigation kicks off in what we'll call the interrogation room, or what chemists formally call an electron ionization mass spectrometer. This is an incredibly common setup for analyzing small organic molecules. Picture an invisible hammer just completely smashing a vase. That is essentially what's happening to our chemical suspect here. As the sample enters the chamber, it gets blasted by a stream of high-energy electrons. It's such a violent collision that it literally knocks an electron right off the sample molecule, while also dumping a massive amount of excess energy into it. This leaves the molecule highly unstable, causing it to rapidly fragment into smaller pieces. Now, if we want to know the weight of that original, unsmashed vase, we are hunting for a miracle. We're looking for the rare molecule that actually survives this chamber intact. We call this survivor the molecular ion. Because the initial blast knocked away a single electron, this surviving molecule is technically a radical cation, meaning it has an unpaired electron and a positive charge. If it can survive for just 1/100,000th of a second, it makes it out of the chamber and to the detector in one piece, giving us the exact molecular weight of our original molecule. Which brings us to part two, hunting the molecular ion. Finding that one single intact piece inside a massive pile of chemical debris is our primary mission as detectives. The machine takes all those charged fragments, accelerates them, and sorts them by their mass-to-charge ratio. What we get at the end is a graph filled with lines representing all the different fragments. When we look at this data, we're basically looking at a chemical fingerprint. For a molecule like benzene, for example, the surviving suspect comes in at a mass of 78. Since the molecular ion is the fully intact molecule, it makes total sense that it should be the heaviest thing we find. By finding that heaviest peak, boom, we instantly know the molecular weight of our sample is exactly 78 mass units. But hold on, we need to be absolutely sure we found the real molecular ion and not just random background noise. It has to follow strict chemical rules. You see, the highest mass isn't always the molecular ion by default. Highly branched molecules can fall apart so easily that their molecular ion vanishes completely. We also have to make sure we aren't measuring background contaminants. And crucially, the distance between the molecular ion and the smaller fragments has to make mathematical sense. Like, if you see a loss of 18 mass units, that perfectly aligns with losing a water molecule. It has to be logical. Let's move into part three, rules of the weight game. The microscopic world is absolutely full of decoys, so we need a few detective cheat codes to verify we have the right suspect. We can't just rely on finding the highest number. We have to use the fundamental laws of chemistry to cross-examine our data. One of the absolute best cheat codes is the nitrogen rule. It's a fast visual trick that immediately tells us if our suspect contains nitrogen just based on whether its mass is odd or even. Nitrogen is a bit of a weirdo. It has an even mass, but an odd-numbered valence. Because of that odd valence, an extra hydrogen atom always ends up hitching a ride, throwing the total mass off by 1. So if your molecular ion lands on an even number, your molecule has 0 or an even number of nitrogen atoms. If it's on an odd number, it definitely contains an odd number of nitrogens. It's that simple. We also got to watch out for decoys, specifically the M+1 and M+2 peaks. These are naturally occurring heavier isotopic twins that show up just slightly heavier than our true molecular ion. In reality, atoms aren't purely one mass. About 1.1% of carbon atoms are carbon-13. So in a huge sample, a tiny fraction will randomly contain a heavier carbon, creating a small peak 1 mass unit higher. And if the molecule has chlorine or bromine, you'll see a massive M+2 peak because heavier versions of those halogens are extremely common. We have to spot these natural decoys so we don't accidentally overestimate our suspect's weight. And finally, part 4, the metastable missing link. Let's look at our most dramatic clue and see how this builds a rock-solid case. Once we have the true weight of the intact molecule, we still need to prove exactly how it's shattered. Metastable ions are literally the ultimate rule breakers. They shatter mid-flight, capturing a molecular disintegration in real time. Normally, an ion breaks before it gets accelerated, or it doesn't break at all. But metastable ions? They have a lifespan right in the middle, about 1/1,000,000th of a second. They survive just long enough to get accelerated, but then they disintegrate on their way to the detector. Because they leave part of their mass behind mid-flight, they hit the detector with abnormal kinetic energy, showing up as these wide, weird, smeared-out decimal values on our graph. Now, there's some math here, but it's not just a random equation. It's the smoking gun. It mathematically links a specific shattered fragment directly back to the exact parent ion it came from. We call the apparent mass of these weird mid-flight breakers m star. By squaring the mass of the newly created fragment, which we'll call m2, and dividing it by the mass of the original parent ion, m1, we should get exactly m star. It's a perfect mathematical match. Spotting this missing link gives us absolute proof. No more guesswork. We don't have to just assume that fragment B came from fragment A. The metastable math proves it beyond a shadow of a doubt. It tells us the exact story of how our chemical suspect fell apart. So, wrapping up this explainer, by just smashing molecules and studying the debris, from that sturdy molecular ion all the way to those fragile metastable fragments, we can deduce the exact weight and structure of the invisible world around us. It really makes you wonder, if we can mathematically reconstruct a shattered molecule flying at microsecond speeds, what other hidden structural mysteries will mass spectrometry solve next? Thanks for hanging out and playing molecular detective with me today.